Hello everybody, this is the new project, but first I'd like to show you my trusty little power supply which I built at home. Here it is. You turn it on and you see in the background on the instrument the needle swung to 10 volts, okay, but I can change it, like I can lessen the voltage or increase it. All right, okay, I'm trying to set it to 10 volts. Well, it's a very cheap and very cheap and dirty power supply, so there is no self voltage regulation inside. And if I connect, for example, a light bulb to it, okay, so it doesn't matter which pole I use. This is one, yeah. Okay, as I connect it, take a look at the instrument. Okay, so it goes down to well below 5 volts, okay? And you see the bulb is lit, but not fully because it's a 12 volt bulb, okay? So, but I can increase it. Okay, so no big deal, okay. But let me repeat it. So go back to 10 volts. Okay, we are going back to 10 volts. Okay, this is the idle voltage. Okay, so this is the highest. I won't touch the potentiometer, but if I connect it to the bulb, it goes down. Yes, because you know, the loaded voltage is always lower than the idle voltage. I think it's elementary, Dr. Watson. Okay, so it's 4 volts, 10 volts. Now, it always happens, but let's check out this other contraption that I put together over here. This is what I'd like to share with you. If you take a look at it, it looks like a Bedini motor with a magnet for a rotor, but this is not a Bedini motor, this is a Joule Thief motor. And for the difference between the two circuits, I'd like to refer you to my video list where I have uploaded 2 videos pointing out the difference, the real difference between the Bedini SSG circuit and the Joule Thief circuit. Okay, this is a Joule Thief circuit. Okay, now let's connect it up. This is the positive input, and okay, we are still at 10 volts. Okay, maybe I should place this instrument over here, over this battery. No, you can't see it, can you? Oh, probably can see it. I can zoom on it a little. Okay, so in the background you can see the battery. Now, as I connect it to the negative, maybe you can see a little blimp. Okay, so sorry, that was a little blink. It happened only once. Okay, doesn't matter. And here you can see a 1 ohm resistor just to protect the Mosfet, because this is a IRF630 Mosfet. It's a power Mosfet, but Mosfets are, you know, very delicate devices, so it better be careful when using them. And here at the background you can still see, sorry, I moved this away from the way. Okay, probably you can see the needle is at 10 volts. All right. Okay, now let me start this. Here is a switch. Okay, so you can see the neon bulb. It's gone into self-oscillation. Now it's self-oscillating. And as you see in the background, the voltage dropped to like 7 volts. Okay, if I turn it off, it goes back to 10 volts. If I turn it on, it goes down to 8 volts, but it's self-oscillating. Now, I'm trying to crank up the magnet inside this little chamber, but I have to hold it down to prevent it from jumping up and sticking to the core. Come on, come on. Okay, it started turning, but take a look at the instrument at the back. So it shows way more than 10 volts. Can you see? Okay, It's much more than 10 volts. Yeah, much more. Okay, and if I turn it off, I'm going to turn off the switch here, down. But as I turn off, take a look at the needle. It went up even further. Okay, now it shows like 17 volts. Okay, so these numbers are calibrated against this other instrument, which is over here. Okay, I'm going to use it later on. So, have you ever seen anything like that before? This is an old school analog instrument. It's nothing, only a swinging coil in a permanent magnet field and a needle moving over a scale, okay? So it shows 18 volts, maybe, okay? Now let's disconnect it and watch the instrument. Okay, stopped. And it went back to 10 volts. How about that? Have you seen anything like that before? Because I haven't. Okay. Now let's start it again. Okay. Okay. So that you can see the whole story. Here it is. Okay. 10 volts in the background. Now I turn it on, self-oscillation, okay? It goes into self-oscillation without the magnet, right? Sorry, no oscilloscope. Yeah. It's like a quasi-theremin. Okay, decrease the volume a little. Okay, if I disconnect it, okay, it goes into static. Now it's self-oscillating. But the instrument shows like 8 volts, okay? Now let me put the magnet and start it. Okay, and you see in the background the instrument shows like I don't know how much, and I disconnect it with the switch. It's even smoother and faster. So it's not self-oscillating anymore, but it produces high voltage spikes, as you can see on the neon bulb, and you can charge batteries with it. Okay, now here is an old battery. I put 2 magnets to the poles, positive to positive, and here we go. Okay, and as I connect it to the battery, the neon bulb goes out and it slows down a little, but interestingly, the voltage in the background is still very high, much higher than the idle voltage, which is a very interesting notion. All right, so now we are charging it with the with the Joule Thief motor. Okay, and there is a magnet inside for better efficiency, and I use diesel to lubricate it. Just a second, I zoom out again. Okay, and here is diesel. I can lubricate with diesel. Yeah, sometimes I do it because I don't want it to brush, this little chamber. But now it's interesting. So it's running, but if I remove the magnet, or the magnet sticks to the core for some reason, take a look at the instrument. What happens? Okay, the magnet goes up, Okay, and it goes back to 10 volts. Okay, so it reverts back to its normal and won't self-oscillate. Okay, now let's go back and turn it on. Now the neon bulb is off because the battery is taking up the spikes. You can, okay, so we can start it even with the battery on. Okay, it's running now, it shows better, and if I stop it, I mean if you turn it off, it goes out to 17 volts, which means very little power is, very little current flows through this MOSFET, and it stays stone cold. Once I had it running for a whole week, and it was very cold. Okay, so hardly any current flows through this MOSFET, and very little power is used in this mode. And so it's walk-away safe, because if you leave it alone and something happens and the magnet falls out like this, it just switches itself off, and so it places itself in a very safe and quiet configuration. Okay, so like an open circuit. Okay, nothing happens. Whereas if I start it with a magnet, okay, oh, sorry, now it goes, and again it's not so efficient, but it's still very good because it shows more than the idle voltage. It shows like 13 volts or 12. Okay, but let's see what happens if the magnet stops for any reason or falls out. You see, the voltage goes down, so it's lower than 10 volts, which means it is in self-oscillation. Can you see? Self-oscillation, and it takes much more power. So if I left it that way in an hour, for example, it would be quite warm. Maybe it would burn itself. Yes, it's a little bit warm, but not really. So it's not really safe. But if the switch is on, I mean the switch is off, then it's absolutely safe. It goes back to 10 volts, which means the circuit is open, no current is flowing. I think it's very clear so far. And there's a little feature, because I was experimenting with this chamber. It's pretty large. Maybe you could use a smaller one, a smaller diameter, and then it would hold the magnet in place. But I found that the friction is too large, probably because of the radii are too close of the ball and the chamber. So this is a larger one, and it spins much more freely. And there is something inside I want to get out. It's a little bit, okay, yeah. So I didn't want this chamber to be, abraded and worn out. So this is why I put this little film. Sorry, other way. Yes, here it is. Okay, so this little film, it's a little bit messy, but so it takes up the friction. Okay, and it's much smoother and much quieter than in the chamber itself. Okay, I just put it inside because the magnet is burning in one spot, and it would maybe eat out the stuff, yeah, the plastic from this spinning chamber or magnet chamber. Okay. And so I put it back again. Yep. And okay, let's check out what else can we do with this. Okay. Self-oscillation. Okay, the needle is down to 8 volts. Magnet spins, and the needle is way above. Can you see that? Yeah, it's way above 10 volts, and if I turn this off, it's even better. Okay, so, and you can leave it, or yes, you can charge the battery like that, so it slows down, but it keeps moving. Interesting. And the needle shows like 18 volts, all right, up there. Don't forget the idle voltage was 10 volts. So it looks like Overunity because it's like pushing, it would push back some current. It's not the case, unfortunately, but it's a very interesting phenomenon. The Google chatbot Gemini suggested it might be to do something with the ripple effect. Okay, I don't know too much about it, but this power supply is very simple. Let me show you the schematics. So actually I took a regular DC 35 or 36 volt DC power supply, and I built my lab supply on top of that. So yeah, okay, I hope it compensates. Okay, so this is the power supply. Okay, this is the transformer. Here is the rectifier. Here is a filter capacitor, and then I used a Z44 Mosfet for voltage regulation, and yeah, 30. Okay, good. And I use an LM317 current limiting chip with a corresponding resistor, and I think it's set to give out 1 ampere maximum. Okay, so it's very simple. So the regular factory made power unit. So this is the mains, this is the secondary, this is the rectifier, okay, full bridge rectifier, and the filter capacitor. It looks like electrolytic filter capacitor. And here is a potentiometer, okay, a 10K potentiometer on the gate of the MOSFET. And here you can see a capacitor for some reason. Yes, okay, I don't know. Yeah, maybe this is just to filter out any noise. Okay, so and it makes the MOSFET more stable. And here is an LM317 limiting current limiting chip, and there is a big resistor. I don't know, it maybe 10 watts. Yeah, okay. So this is 1.12 volts. Okay, okay, yes. And here is the output. Okay, now. So it's nothing to it, it's really simple. Okay, as you see, it charges the battery. Okay, now I won't bore you with that. And here's a small battery, a small lead acid battery. Yeah, it can charge that too. Yeah. Okay, and it won't even lose too much power or speed. Okay, probably because there are several cells. Okay, with an AA battery, there is only one cell. It's a big 1.5 volt cell, and mind you, these are non-rechargeable batteries, but you can recharge them, not fully, not 100%, but these circuits okay, won't heat up the battery, because then it is damaged and it's dangerous. There's a danger of fire or something, or splittering or exploding. But they don't explode because they don't warm up. No, they're totally cold. Okay, so the one that I was charging is totally cold. Okay, here you can try to de-sulfate these batteries, these old batteries as well. And so this is a pretty good contraption. Now, let me disconnect it and move it away. All right, good. So actually, let me set the camera a little bit. Yeah, okay, it's a better angle. Good. So at the top you can see this heatsink, and there is a MOSFET and two neon bulbs that only one seems to be working, which is placed on the drain and the source. Okay, so there is one on the source and the gate. It doesn't seem to be working. In the past it did, I don't know, but it works. Okay, so it didn't kill the MOSFET. And here is the run coil, which is hand wound. And so these are all the, you know, band-aid or elastoplast form. sorry, I'm trying to find the schematics. Yeah, lots of projects everywhere. Sorry. Please bear with me. Yeah. Yeah, lots of projects going on. Yeah. Ah, yeah, it was there. Sorry, I should have put a bookmark in it. No, it's not here. Unbelievable. Gee, I don't know. Probably it will be other end. Okay, but very well. Okay, so this is a 1.2 ohm coil. It's filled up. Okay, I think this elastoplast or whatever you call it, or plaster, was empty, and I filled it up with copper wire. But this is a single, so it's not a bifilar, it's just a single fire or a unifilar coil. And the trigger coil is down here, okay? So this is a solenoid which was salvaged from a discarded, I think, a washing machine or dishwasher, okay? So these solenoids are very common in those household devices. And yeah, and here is a potentiometer with a resistor. Okay, I don't use the potentiometer; it is not in use anymore. But maybe you can. Okay, so maybe change a little. Okay, I decrease or increase. Okay, maybe in the back. Sorry, I'm not a very good cameraman. Okay, so here's a potentiometer. If I turn it up and down, maybe you can see the needle move a little. Okay, so it changes the efficiency. If I lower the resistance to the gate, so the voltage goes down. If I increase, the voltage goes up. But if I disconnect this potentiometer, then it really gets off the ground. Okay, because it really flies now. Because the switch actually just disconnects this potentiometer and the resistor from the gate, okay, between the trigger coil. I'm going to point out it on my schematics, if I find it, that is. But you can't start the system without the resistor. But when it's turning, when it's active, you can disconnect it, and then it further increases. It's like a turbocharger on a motor, okay? So it won't work at low RPM, but when the motor is really revved up, then the turbo fan kicks in, I mean the turbocharger, and then the engine really starts to output a lot of power, or put a lot of power. And yeah, sorry. Maybe I should stop it or pause it. Just unbelievable. Multi Mosfet. Current yeah, it's a current power supply, isn't it? Whatever. No, maybe I'd better pause it. Sorry. Yeah, sorry about it, guys. Finally, I found the schematics. Yeah, here it is. Okay. So at the top, you can see the run coil. It's 1.2 ohm, and the trigger coil is 1.2 kilo ohms. Okay, so it's much finer. This is the trigger coil, but this is an air core coil. Okay, so here is a little bolt you can see, because I installed a nut inside this air core coil, and I can turn this bolt and bring it closer or further from the magnet, because I found that sometimes it starts swinging. Okay, and this is pretty much unstable. So this is a stabilizer screw or bolt. Okay, because if it's too close, then it pulls down the magnet too much, and then it slows down because the friction increases. But if it's too far, it won't hold and stabilize the swinging. Okay, so this is why I put it in. And you can also change the angle of the trigger coil, but I think this is best here. Okay, so you can experiment with it. And there is a big bolt at the back, and you can move it up and down and figure out the distance from the main coil, because if it's too close, chances are that it just attracts and pulls the magnet to the core. Actually, this is a ferrite core which I took from a flyback transformer, and there are broken parts, so I pulverized it and I glued inside with some lacquer. Okay, so this is it. Sorry about this crappy implementation, but I was interested in the effect. Okay, so not the design. Okay, so back to the schematics now. Sorry, this is the lower part. Okay, so disregard the top. Yes, and so this is the positive. The power goes through the main coil to the drain, and then the source back to negative. But here is a resistor. This is a 1 ohm resistor. Here is a bigger one. This is a 5 ohm resistor and 5 watts as well, as you see. Okay, this is a 1 ohm resistor. This is a 5 ohm. I'm going to use it with the car battery, because when I tested it on the car battery, this inrush current killed my MOSFET, and so I found that it's safer if I use a voltage divider resistor, which is right here. Okay, now so the positive is also connected via this red cable to the trigger coil, and the trigger coil actually goes through this switch, the variable resistor, and this 1K resistor. Altogether it's 5K. Okay, but if you use a 5K resistor, it doesn't matter, because I don't use this potentiometer. It's just there for experimenting, and but across this resistor and switch, there is this 1 microfarad capacitor. Okay, so it's a foil capacitor, but I think you can use other kinds of capacitors. And this switch actually disconnects the resistor and the potentiometer, and then the signal goes through. Now the signal goes through only the capacitor. If I turn it on, the signal goes through the resistor and the capacitor, but the efficiency drops. In the background, again, you can see the voltage is like 15. If I disconnect the resistor, it goes up to 17, 18. Okay, so it's much better. Okay, and it runs very smoothly, so it's no problem there. What else is here? Okay, so the neon bulbs are here across the drain and source, and there's another one across the gate and source, and there is a pull down resistor, which is, I think, 12K. Okay, so a 12 kilo ohm resistor is somewhere. I don't know, you can't see it, but this is a pull down between the gate and the source. So the MOSFET needs a pull down resistor, because it can stay, floating, because the voltage just charges up the inner capacitor, and it stays there, and then it closes the circuit between the drain and the source, and it's not very healthy. So it's always advisable to use a small pull down resistor. I use the 12K pull down resistor. Okay, what else can we see here? Actually, this is it. Okay, now let's stop it. Disconnect. Okay, let's disconnect it. I turn off this power supply. Okay, and oh, sorry, I wanted to show you something, so I connected back to the circuit. Okay, you see the needle goes down very slowly because of the filter capacitor discharges quite slowly. Okay, but now I turn it back on, and it jumps back to 10 volts. 10 volts, right? Now, okay, again, I'm gonna crank this ball here. Oh, if I manage, not so easy. Okay, now it's up. Okay, let me reposition myself. Okay, good. For some reason, it won't start now. Interesting. Jesus. You know, the problem is that I forgot to turn on, yes, to turn on the resistor, okay? So with the capacitor you cannot start it. I demonstrated against my will, but now, okay, so it's easy. It runs, okay? So, and once it's picked up the speed, okay, you can disconnect it. The problem was that the switch was off, okay? And with the off switch, you couldn't possibly crank the engine, I mean this motor. Oh, it stopped for some reason. Okay, let me find it. Hasn't done this before. And maybe, okay, there's another feature I wanted to show you, because here at the back, yeah, okay, let me show you. Here at the back, you can change the angle at which it is tilted, okay? So maybe I change the angle of the contraption. You can see this support and with a little counterweight at the back. And now it is, I change the angle. This is also a factor that you can play with. Okay, yeah, and now it turns. And here I use a little diesel oil, okay? This is the best lubricant I found. Okay, just a little, just a drop is enough, okay? You can use water, you can use mineral oil or lubricant oil, but the lubricant oil is pretty viscose, so it holds back the magnet, and it's not the best. Okay, maybe I can turn it out a little. I mean this stabilizing bolt. Okay, now you see it's swinging from side to side. Okay, so maybe I turn it back a little more. Okay, now it stopped. Okay, so you have to find the sweet spot so it holds the ball quite stable without pulling it down too hard against this little foil that it's turning on. Okay. Now, as you see, it shows like 17 volts, but in reality it's not that much, because now I'm going to connect another instrument to measure the output. Okay, so maybe you can see, where is it? Sorry, yeah, it's here. Okay, you can see this here. Now I'm going to connect it to the negative, and you can see the instrument at the back, the needle, and the instrument, the digital instrument here. And as I connect it onto into the circuit parallel with the other instrument, you see it goes down to 7 volts, and the needle also goes down. Okay, so 6-7 volts. Okay, so this is logical, but still I don't understand why the analog instrument shows so much more voltage than the idle level. Okay, so it's interesting. Anyhow, I'm going to stop it now. Okay, let me stop it. Very good. Turn off this power supply, and I disconnect it from this resistor, and I'll change. Okay, so this little clip goes to the gate. Okay, and here there is a 5 ohm resistor, so it's a little larger, and I'm going to put the negative. Oh, sorry, I forgot the cables. Please bear with me. Has it stopped? Okay, so okay, I found the cable. I'm in the lead. In the background, you see this large battery. Okay, so this is this Elgo handicap, you know, scooter or something. There are two of them in this vehicle, and it's not very good, but it's good for experimenting with. And now I connected it to the circuit, and yeah, here is the positive. Maybe you can see a little blink as I connected up. Okay, maybe you saw the blink. Okay, now I changed the configuration. Instead of using this 1 ohm resistor in the back, okay, now you can't see it, for here it is because of the clip. Here is a 5 ohm. Okay, so I just make sure they don't touch. Okay, and here it is. Okay, now let me try it. Now it's on the 12 ohm battery. Probably the battery is very powerful. Okay, so it can deliver any kind of current, and the inrush current is not very healthy for the MOSFET. It's quite delicate, and this is why there's this voltage divider resistor here. Now let me try to start it. Okay, now it works fine. You see in the background it's a little bit higher than 12 volts. Maybe it's 13 already. Yeah. Okay, so it goes much faster because of the voltage is higher. And if I disconnect this, okay, it moves fast. So no extra voltage. Okay, so this is the story. Okay, it would have been very nice if it had back charged the battery, the run battery. It just doesn't happen. Okay, but you can still use it for, you know, charging things. You can even short them. Okay, interesting. If you short it, okay, it slows down, but it doesn't really decrease the voltage. Okay, it's still going. Sorry, it's shorted. Okay, it goes up. Okay, so this is the negative lead, and if I touch it to the positive, it's really shorted, and it slows down the ball, and maybe you can hear this humming voice, but still it runs. All right, so it's a very robust charger. Okay, stone cold. Now, okay, now it runs on the battery. What is there? Oh, okay, so this is the frequency. I don't know, maybe a 2,000–3,000 hertz. I don't know. Okay, so this is all I wanted to share with you guys. And again, this is a Joule Thief circuit, and see my other videos about the differences between the Joule Thief, the real difference between the Joule Thief and the Bedini SSG circuits. These videos are not for entertainment. I'm sure you can draw that conclusion by now, but I think it's interesting content. Okay, so keep well, all the best, and peace.